So let's get started. So today we are talking about prototypes, papers, and productions, and how we built our purging system at Fastly. So I am Bruce Spang.
And I'm, right, microphone is here. And I'm Tyler McMullen. Bruce is an engineer at Fastly. I'm the CTO of Fastly. Yes, Fastly. So you probably already know what a CDN is, but because this is velocity, honestly. But bear with me for a moment, because I'm going to explain anyway. So a CDN is a content delivery network. It's a globally distributed network of servers. And at its core, the point is to make the internet better for everyone who doesn't live across the street from your data center. You might use it for images, for APIs, or for websites. For instance, this website about how much GitHub loves Fastly. Don't worry, I'm not actually going to, this isn't really going to be a sales pitch, don't worry. Or you might use it to serve up something like this image of a tweet of terrible advice. And you'll see why I'm putting this tweet up here as we go along. But just to read through it real quick. Distributed systems don't read the literature. Most of it is outdated and unimaginative. Invent and reinvent. The field is fertile, really. And I blacked out the name of the person because I would be embarrassed of that. So our goal is to deliver whatever your users are requesting as quickly as possible. To do this, we have a network of servers all over the world. Suppose you live in Australia, and you want to visit a site which is hosted on servers in New York. Normally, you would go directly to this site halfway around the world, and it would take quite some time to do that. Note that this is actually a greatly simplified version of this. In reality, you would probably bounce between 20 or 30 different servers in the least straight route that you could possibly imagine. Right, with Fastly, instead, you would go to one of our servers and say Sydney there. Normally, a copy of the website with the particular content you'd be looking for would be on that server, and it would be much faster. But if the content isn't already there, we could request it from other local servers. But ultimately, if it's a new piece of content, or it just doesn't happen to be on our servers yet, you may still have to make a request back to New York. However, next time you or someone else visits the site, it would be stored on the server in Sydney, and would be much faster, right? Basic CDN stuff. So, purging. Once a site is stored on the server, you might want to remove some piece of that content for some reason. We call this a purge. For example, you might get a DMCA notice and have to legally have to take it down, or it could be something as simple as your CSS has changed or an image changed or something like that. However, one of the points of Fastly from the very beginning was to make it possible to purge content really quickly. For instance, The Guardian is caching their entire homepage on Fastly. So when a news story breaks, they need to be able to update that page as quickly as possible. So the purge needs to get around the world to all of our servers as quickly as possible, and it needs to do this so reliably. So we actually had 3 different versions of the system since we started. So we're actually going to walk through the 3 different versions, talk about why they worked, why they failed, and so on. So step 1 was let's make the simplest possible thing. Our syslog. So this might be somewhat surprising because people who have used our syslog would not necessarily think, oh, this would be a great way to build a purging system. However, it was something that was already stored on our servers, and at its core, our syslog is actually just a message queue, right? So let's walk through how this actually works. We have a bunch of edge nodes spread around the world. Let's say that A is in New Zealand and F might be in Paris, let's say. So a purge request comes into A. Purge could be for any individual piece of content, whatever it is. That forwards it back to our central rsyslog broker, which is in Z, which might be in, say, Washington, D.C., right? And the broker ends up sending it to each of the different edge nodes. This probably looks pretty familiar. It's really the simplest possible way of solving this problem. We got this done really quickly, and it worked for a little while. The primary reasons we did it this way, this software was already actually deployed on all of our servers. So we just had to write a new config file, write a little Perl script, and we're done. Really simple. One of the nice things about the system is that it's really easy to reason about. At its core, it's just a message. It's just a way of sending messages via TCP in a relatively reliable fashion, right? So why does it fail? Well, for one thing, high latency. If you have 2 servers that are sitting right next to each other, instead of one sending the purge to the other, you actually send it back to the origin like back to that broker in Washington, D.C., and then have to bounce it all the way back to send it to that one server that's right next door. It's also incredibly partition intolerant, right? That central broker is a giant single point of failure in the system. Additionally, it's also the wrong consistency model. This system has much stronger consistency guarantees than we need or want. For instance, like I said, it uses TCP, which guarantees in-order delivery. But how does that actually affect the behavior in production? Well, let's walk through that real quick, a very simplified version of it. So let's say we're sending 1,000 messages per second, one message every millisecond. Let's say the node we're sending to is 200 milliseconds away. That means that at any one moment, there's about 200 messages, 200 packets, let's say, that are actually live on the wire. Let's say a packet gets dropped at the very last hop before you finally make it to the server that you're sending it to. Well, instead of having that one message be delayed, what actually happens is the rest of the packets continue to go through, but are buffered in the kernel at that actual destination server and don't make it to your application yet. The destination server then sends a SAC, a selective acknowledgement packet, back to the origin, which effectively says, hey, I got everything from packet number 2 to packet number 400, but I'm missing packet number 1. So while that's happening, the origin is still sending new packets, which are still being buffered in that kernel at the destination server, right? Yeah. Then finally, the origin receives the selective acknowledgement packet, realizes the packet was lost, retransmits it, right? So what we end up with here is 400 milliseconds of latency added to 600 messages, all because of one dropped packet. Each of those could have been delivered as they were received, and we and our customers would have been just as happy with that, possibly happier, but instead they're delayed, right? So this is clearly the wrong consistency model for this system. So, version 2 of the system. Make it somewhat more interesting. In this one, we're attempting to figure out a better way to do this, to fix some of these problems with it. So we started out, I'm going to read some papers. Right? So I read up a bunch of papers on atomic broadcast. It seemed like the closest fit to what we're actually trying to do with this system, right? We're trying to send messages to a bunch of things in a reliable manner. So we read ZAB, we read Part-Time Parliament, which is the Paxos paper. Then we read all of the papers that explain the Paxos paper and all of the papers that explain those. But essentially, this has the same problem. The guarantees are still too strong, right? So it still has the problem of, like, if you send one message, doesn't get through, all of the other ones still don't make it. So at this point, I really need to fix the system, really need to make it better. And so instead of continuing to read papers, I thought really hard. And this is kind of the point of that original tweet, which is don't read the literature, just think real hard. We're going to talk about where that goes poorly. So here's a system that we ended up developing to try to fix this. What we do is we define a graph of responsibility that is overlaid on top of our network of servers. So this graph of responsibility defines which nodes are responsible for making sure which other nodes stay up to date with all of the messages. So in this case, A is responsible for B and D, B is responsible for D and E, and so on, right? So purge comes in to A, let's say. A immediately forwards it just via simple UDP messages to all the other servers in the system. Just quick broadcast, whatever. Each of the servers that receives it sends a confirmation to the servers that it knows is responsible for it. Great. But what's more interesting is what happens when a message fails to reach a server. So in this case, let's say it comes into A and doesn't actually make it to E. So what happens is it'll start, the servers that are responsible for the server that has dropped this message start sending it reminders because they haven't gotten a confirmation yet. So in this case, D and B will start sending reminders to E until it confirms that, yes, it did in fact receive this purge at this point. You can think of this as like a really primitive form of like active anti-entropy and like the most primitive form, like primordial stage active anti-entropy, which is a mechanism to make sure the servers are actively staying up to date. So we ran a system fairly similar to this. Obviously, like there's more to it than that, but we ran the system for some time, and again, this works, right? At its core, it's like way faster, right? This is, it gets us much closer to the theoretical minimum latency that we could do this at least for the happy path, right? However, there are problems with it. For one thing, arbitrary partitions happen. The graph responsibility has to be designed very carefully to avoid having common network partitions actually separate the graph completely. even if it's carefully designed, it still actually can't handle arbitrary partitions. The best way to get close to fixing them is by increasing the number of nodes that are responsible for each other, but of course that increases the load on the system as well. Another problem is that this has an unbounded queuing problem. Every node is responsible for keeping other nodes up to date, which means it needs to know what each of its dependents has seen, which means if a node is offline for a while, that queue grows and grows and grows and grows. Finally, the end result of that is actually failure dependence. One node failing means that multiple nodes have to spend more time remembering messages and trying to send reminders to other servers, which means that they, under load, are then more prone to failure as well. So there's a huge problem with failure dependence in this system, which points to the problem of thinking real hard and attempting to solve distributed systems problems. The problem with this is that we didn't manage to find the existing research on the problem, and it turns out that this type of system was actually described in papers in the 1980s, when Devo was popular. The problems that we found with it are actually well known then, if we had found these papers and read them. Luckily, right around that time is when the venerable Bruce Spang started working with us, and so he is going to explain the third version of the system.
So as Tyler said, this is where I came in, and I started working on building the third version of our system that tried to scale better to more servers and higher throughput, and solve a bunch of the problems with the previous system. So I started working on this problem, and I realized that I am, at my core, I'm incredibly lazy. And as Tyler showed just now, inventing distributed systems is really hard. Even though he came up with an awesome idea and implemented it well, it still had a bunch of these problems that have been known about since the 80s. I didn't want to think really hard again and come up with something 5 years later. And I could do a little bit more work and maybe come up with something from the late 90s or something wild like that. So I sat down and I decided to read some papers and see if we could figure out how to solve this problem. Because we had this system in production that was working well enough, we had a bunch of time that we could use to dig into the problem and really solve it well. So Tyler talked a little bit about why you might read papers to do this, and I'll talk a little bit more. So for the first reason, of course, is that papers are super cool, and if you read them, you will also be super cool. You will be able to impress your friends, and it'll be great. You also get a better sense of the problem you're trying to solve. You can sort of understand the bits that make it difficult, and you can get a clearer sense of how you might go about solving it. You can learn about other ways people have tried to solve the same problem and get more ideas. A bunch of papers might tell you that a particular thing is physically impossible to do in a distributed system, or tell you that a particular implementation of a system would be a really bad idea, like these papers from the 80s told us about our old system. If you read these papers, you can avoid a bunch of time trying to build a system that does something impossible and trying to debug that system at 3 in the morning when you get paged. And then finally, if you're super lucky, some papers might describe an actual solution to your problem, and you can just implement them directly and be done. So we decided to read some papers. And we did this by just searching some sort of relevant terms, like send a message to a bunch of servers on Google Scholar. And the first area of papers we found was this area of research called reliable broadcast. And so reliable broadcast is this problem of sending a message to a bunch of servers and guaranteeing that the message is delivered, which sounded to us a lot like our purging problem. So these were papers from the 80s, like an efficient, reliable broadcast protocol and a scalable, reliable multicast. And as it turns out, these papers were all a lot like our past version of this system. They all used this sort of retransmission method to resend messages. And they all had this sort of clever way of building up a graph of doing the responsibilities. But at their core, they were similar. And so this means that they had similar problems to our old system. So I kept looking for new papers and papers that cited these papers that we found and so on, and tried to find a new sort of research that might solve the problem a little bit better. And after a while, we came across this class of research called gossip protocols. And these were written in the late 90s up until pretty recently, now. These are stuff like the plum tree paper or the sprinkler paper, which is great, and it was written just last year. The main difference between these sort of papers and the reliable broadcast ones is that they were designed to be much more scalable at their core. So they can scale up to tens of thousands or hundreds of thousands of servers and deal with hundreds of thousands or millions of messages per second, where the previous ones, the reliable broadcasts, could really only do a couple hundred. And the way they do this is with a sort of probabilistic guarantee instead of a strong guarantee. So instead of like ensuring that a message will always be delivered, they just ensure that a message will be usually delivered. And that's a little bit scary, but we'll talk about why that's okay later. So after reading a few of these papers, we found this one called Bimodal Multicast, which was written at Cornell in 1999. And we absolutely loved it, and it's the one we finally implemented. So here's a sort of a high-level overview of the bimodal multicast algorithm. It's split into two phases, a broadcast phase and a gossip phase. In the broadcast phase, we're just trying to send the message to all the other servers as quickly as possible, and we don't really care if the message is delivered or not. So in this case, we have 3 servers, A, B, and C, and 3 messages, 1, 2, and 3. And in the broadcast phase, we'll just send out all 3 messages as quickly as possible. But for whatever reason, B won't receive message 3, and C won't receive message 2. So to deal with this, Bimodal Multicast has a gossip phase. And the way this works is periodically, every server will pick another server at random and send that other server a list of all of the messages they know about. So for example, A will pick B and tell B that it has messages 1, 2, and 3. B will pick C and tell C that it has messages 1 and 2. And C will pick A and it says it has messages 1 and 3. When a server receives a digest, it'll take that digest and compare it to its own internal state and check to see if it's missing any messages. So B will notice that it's missing message 3. C will see the 1 and 2 and see that it has 1 and 3 and notice it's missing message 2. And A notices it's missing nothing. So then the servers that notice they're missing some message ask for those messages to be resent. So B asks A to resend message 3. C asks B to resend message 2. And at the end of this round, everyone is up to date, and the message has been delivered everywhere. Before I go on, are there any questions about how this thing works? Because the rest sort of assumes you might understand this. Yeah, absolutely. So if in the initial broadcast phase, if none of the other servers receive the message, so the way we solve that is the initial message, when it receives it, it'll keep it around in its memory for this gossip phase, and it'll gossip about it for a long time. And eventually other servers will receive those messages and so on.
Presumably this only works for unordered messages. Presumably this only works for unordered messages.
Yes. Yeah. So the point was that this only works for unordered messages, and that's totally true. So 2 things about that. One is purges for us are totally unordered, so it's fine. And the other one is that you could layer an ordering guarantee on top of this. So you could get in order by the sender, for example, but you couldn't get globally ordered messages. Right. So the question was about like network problems and whether those would still work. Is that okay? So I'll get to that on like the next slide. Any other questions? Awesome. So we read this paper, and we saw this algorithm, and it sort of made sense a little bit. And we wanted to get a bit more of an intuition about how it would work for when there's many servers, and when there was network problems and stuff like that. So to do this, we came up with this simulation to see how the thing would work. So in the simulation, we have 100 servers. Each circle represents a server. And we're going to send a message and try and see that it's delivered. The green circles are servers that have the message. The white circles are servers that do not have the message. We're going to run the gossip phase over and over and over again. A server that has the message will pick another server. And if that server hasn't received the message, it will be resent, and we'll see an arrow go between them. So what we would like to see is all of the servers become green relatively quickly. So let's see what happens. You can see the messages being resent. And pretty quickly, all of the servers have the message. So even though there were a lot more servers here than just 3, it still works pretty well. And so this was a nice sort of intuitive thing that this thing would actually work. But we wanted to be a little bit more rigorous than just running a simulation and being like, yeah, it looks good. And the paper has a bunch of math that tries to quantify the likelihood that a message will be delivered everywhere. So on this graph, the x-axis is the number of rounds of gossip that have occurred, and the y-axis is the percent of servers, not the number of servers, the percent, that have received the message. And so initially, just like 1% of servers have received the message. And as the number of rounds of gossip increases, the number of servers with the message also increases. And after about 10 rounds, about 97% of servers have received the message. So this is pretty cool. And this is a good estimate to us that this thing will work pretty quickly, even though we're picking servers at random. So we started implementing this. We thought it'd be great and started working on it. And we ran across this problem, which is that computers have a limited amount of space which they can use to store these gossip messages. We don't want to have these huge unbounded queues that caused the problems in our last system. So to deal with this, the system has to throw away messages at some point. But it needs to keep messages around to be able to recover them for other servers that may not have received them. So we somehow have to figure out when to throw a message away in the hopes of delivering it everywhere. So the way the paper solves this problem is they'll keep around a message for 10 rounds of gossip, and then they just throw it away. And this is a little weird, but it makes sense when there's low packet loss. So on this graph we saw before with the expected percent of servers, after 10 rounds of gossip, about 97% of servers will have the message. So this is basically almost all the servers. But this is with zero packet loss. And we don't work with zero packet loss, we work with real computers, and real computers are terrible. We see high packet loss, and we see network partitions, and we see them all the time. If this system doesn't work during these conditions, we will have problems. So here's the same graph as before. This time, this blue line represents the percent of servers that have a message when there's 50% packet loss going on. And after 10 rounds, only about 40% of servers are expected to receive the message. So if we threw away a message after 10 rounds, we would expect it to not get to most servers. And this means we'll probably lose purges during network problems, and we'll have to answer a bunch of customer support tickets, and we couldn't really sell this as a service we're comfortable with. So we tried to figure out a better way to solve this particular problem. And what we realized was that the reason the paper threw away messages after 10 rounds was based on the digest that it was using for gossip. So we believe the paper was representing the digest as a list of messages. So it'd say, I have messages 1, 2, 3, and so on. And to bound the size of this list, they had to throw away messages after a few rounds. But what we realized is that the digest doesn't have to be a list. We can use any data structure we want to represent the digest as long as another node can understand it. So what we do is we send ranges of IDs of messages instead of a list. So a server might say, I have messages 1 through 3 and 5 through 1,000,000, instead of having to list all of those out. And this is great because it lets us represent these digests with usually just a few integers. And so this lets us keep a message for a much larger number of rounds. In our system, we keep it around for about 80,000 rounds, and the digest normally stays very small. So if we go back to the graph, this time with 80,000 rounds of gossip, and the blue line this time, a little line over here, is about 99% packet loss. After 80,000 rounds, we expect basically every single server to receive the message. The probability that one doesn't is extraordinarily low. So even though this is just a guarantee with high probability, this is a super high probability, and we're totally comfortable with this guarantee. So all that was a bit about how the system works in theory, and that's great, but it's also cool to look at how it works in the real world. So here's some graphs and stuff about the behavior we've seen in production. So one of the things we care a lot about is the time it takes for a purge to be delivered, because customers are using this to update their homepage, for example, and they'd like it to be fast. So here is a graph of the 95th percentile purge latency. Along the x-axis is the latency. Along the y-axis is the percent of messages with that latency. So you can see some servers have a latency of around 50 milliseconds. A bunch more have around, 120 milliseconds. And what we can see from this graph is that the 95th percentile latency in Tokyo is usually just about network latency to all the other data centers. It turns out that these spikes in the latency correspond about to the other data centers spread out. We can look at this for all our other data centers. New York is really centrally located, and network latency is only about 50 milliseconds maximum to anywhere else. And so we see purge latency be about 40 milliseconds on the 95th percentile. London and San Jose are a bit farther from each other, so the purge latency is about 80 milliseconds on the 95th percentile. And Tokyo is the farthest away from everybody, and that's about 150 milliseconds. But again, all of this is just about the network latency. We're not seeing this high packet loss and this retransmit. But when we do, the graphs look a lot more interesting. So when we were first deploying this system, we had to punch holes in the firewalls in all of our data center so that the servers in the data center could communicate with the outside world. In one of these data centers, we messed up the configuration, and 2 of the servers in the data center couldn't communicate with the outside world at all. They could only communicate within the data center. And so this was a sort of classic network partition, and we hoped that the system could handle it. And so these are graphs from during the problem. The left graph is the 95th percentile latency. The right graph is the throughput. The blue lines are servers in the data center that were not affected by the partition, and the red and orange lines are servers that were affected. The partition starts when the latency on the affected server jumps up much higher to about 10 seconds. So the partition was definitely affecting these servers. But if we look at the throughput for all of the servers, it looks to be about the same. So even though these servers couldn't communicate with the outside world at all, they were still able to recover from the other servers in the data center quickly enough that we couldn't really tell the difference. So this is a pretty good sense that this thing actually works during normal network problems. Here's another network problem we saw. Right before I was giving a talk on this a while ago, I looked at the graph to see if anything interesting was going on. Turns out there was some major packet loss in the Asia and Pacific region, just casually in the background. Here are the graphs again. On the left-hand side is the number of messages recovered by the system over time. On the right-hand side, again, is the throughput. The red line, which is the spiky one over here, is a server in the Asian Pacific region that was affected. And the blue line, which is not over here, but you can sort of see there, is a server in the United States that was not affected. And so even though the packet loss over here works out to be about 30% of the throughput during this time period, the throughput is almost unaffected. You can't really tell the difference between a server that was affected by this high packet loss and a server that wasn't. So again, this is a nice indication that it normally works. The coolest example we have was this denial of service attack a few months back against one of our private customers. So we have these customers that we'll send servers to, and they'll put these servers inside their own network and serve traffic from them. One of these customers underwent a pretty severe denial of service attack, and their network was totally unreachable. We couldn't ping our servers in the network. We couldn't SSH into our servers in the network. It was just gone. And so we looked at the graph, and we expected to see the purging system totally fail, because the servers were unreachable. On the left-hand graph, again, is the latency for the purges. The spiky red line is the victim of the DDoS, and a blue line was a public server that was unaffected. And when the DDoS starts, we see the latency jump up to 60 seconds at some point, so it's definitely having a severe effect. But if we look at the throughput, we can see that, again, it definitely affected things. There's a big spiky line for the affected server. But if you sort of squint at that line and maybe average it out a little bit, it looks to be about the same as an unaffected server. And when the DDoS ends around 10 minutes, we don't see a huge spike in the number of messages recovered that would indicate that it wasn't able to recover some during the time. So even though we had this server that was completely unreachable during this attack, this system was still able to recover messages quickly enough to stay sort of roughly up to date. So this is great, right? Even though we have these crazy network problems, the thing will still work. So why might you care about this thing? What are some takeaways for building systems of your own? So the main thing we learned is that good systems are boring. We can go home at night, and we don't need to worry about this thing falling over due to network problems. We don't have to be woken up at 3 a.m. and have to log into the server and debug this distributed system. And we've been able to increase the number of purges we do by about an order of magnitude without having to rewrite these huge parts of the system. This thing just works, and it's great. So here's Tyler with other stuff we learned.
So right, this is great for us, but again, why do you care about how we built our purging system? So this kind of comes back to a point that I was making earlier, which is, this is supposed to be a sponsored talk, right? But instead of trying to sell you one Fastly, the reason we're actually giving this talk today is as more of a public service announcement. Don't heed advice like this, please. Please don't go and invent handcrafted, bespoke, distributed systems. Certainly spend the time inventing and thinking, but don't ignore the research. It would have taken us quite a lot more trial and error to come up with a system that we're as happy with now and in the future, if it hadn't been based on solid research. And because we did, now we also have a good foundation to invent new and actually original ideas on top of, rather than reinventing systems from the 80s. So, essentially, if you take away one thing from this talk, remember this one weird trick to save yourself 20 or 30 years of research work. Please read more papers. Thank you. Questions? No questions at all? Indeed. Okay, well, yes.
In your simulations, would the up or down of the number of systems that it has actually talked to before it turns into the latency is too high? Did you ever try running it at like 10,000, 20,000, 60,000 systems?
So the question was, what happens when the number of servers actually increase dramatically? Instead of being 100, what if it's 10,000 or 100,000 and so on? Bruce.
So Tyler actually asked me this question when we were preparing, like, what's a hard question someone could ask? So thanks for asking it. The question is basically like how the gossip is affected by the number of the servers in the system. And so because we're using these sort of smaller ranges, like just 2 numbers to store a large range, we can pack a lot more servers into one gossip message. So right now we have a few hundred servers gossiping, and we can fit it easily into a few UDP packets. And we expect that we could do a few times more than that, like 5 or 10 maybe, before we start running into problems with the size of the gossip packet. But if in the future, we wanted to deal with like hundreds of thousands of servers, there's a few things you could do. Like you could only gossip to a few servers, and then sort of let it spread out that way. You could hierarchically structure servers, so some servers gossip with other data centers, and then in the data center, they gossip with each other. So and there's sort of ideas like that.
But if your question was more about how it actually affects like whether or not servers receive things, the percentages don't actually change regardless of the number of servers that you have in the system. So we would expect roughly the same amount of like time for it to take. Anything else? All right. Please stop by our booth.